So after our introduction to forces, we're going to do force diagrams. Okay, so there's lots of force diagrams we're going to go through. So we can represent them using an arrow, and this is the magnitude. Remember, it's a vector quantity. It's got a magnitude and it's got a direction. Okay, they can represent three bits of information: the strength of the force, depending on the size of the arrow; the direction of the force, depending on which way the arrow is going; and the point at which it acts. Okay, so you usually we'll talk about examples of what you do with different things as we go through. Force arrows must always act on something, so the tail of the arrow must be anchored to it. Okay, so look here, the weight is acting from the center, that's okay. Okay, it's separate from the actual object, not okay. Okay, it's underneath the object, and again, not okay. Or it's touching the object and you see it's on the object there, it's reacting from the base, that's okay. Okay, so it has to have some form of contact with the object. Now remember, we have contact forces and non-contact forces. So contact forces act on the point of application where the surfaces meet. Okay, so you can see them here, there's where the surfaces meet. So let's put the arrow where the surface meets here for friction, or for pull. We know the pull is pulling it in that direction, so we can connect it to the side here. Friction is where the level is here, so we've got to put the arrow where it is. Non-contact forces act through the center of the body, so generally just put the arrow on the center of whatever it is. So contact forces, the point of application where the surfaces meet, for example at friction, or if you're pulling it in a certain direction, the point of application, so I'm pulling it from there, so therefore the arrow goes there. Now, multiple forces will act on a body at the same time. And we represent all the forces acting on a body by drawing a force diagram, also called a free body diagram. Okay, and that shows the forces acting. So let's have a look at one. Here's an apple on a desk, and we've got 4 newtons going downwards. This is our gravity. You can see up there is our gravity. Okay, and this causes a reaction force. So two forces you can hear going in opposite directions. Now, the weight and the reaction force, okay, from the table. So the reaction force is the table coming up, and we've got 2 forces acting in opposite directions. The table, the reaction force to the apple that is on the table. So here's your purple reaction force, and here is your gravity, are equal. Because they're equal and opposite in size and direction, okay, we can draw a free body diagram. So let's have a look. Let's get rid of the apple and get rid of the table. And there you go. There's a free body diagram, a lot simpler, okay, and just shows them work in those directions. And there's your representation of your apple, essentially. Okay, so let's look at a skier next. So a skier, what are the forces acting on a skier? Well, first of all, they're going downwards, so there must be gravity involved. So there's your gravity pulling down at 500 newtons. Okay, and then we have the reaction force from the snow, from the land, going up at 400 newtons. And we have the friction, which is 300 newtons. Okay, so that means we can draw a free body diagram of this as well. Okay, so let's draw that free body diagram there. And you can see we're doing it in the right direction, and we're showing the levels of newtons, or the number of newtons at each point. And this eventually would cause that skier to go down, because you can see this force is larger than this force, okay? And that's causing it to go down the hill. Now, a car on a road. You see a car on a road, this time gravity is pulling it down at 9,000, okay? But the pressure, the reaction force on the wheels is 4,500 N each time. Okay, the driving force is 2,000, but again, we've got some air resistance going on, which is 250, and this is air resistance, also called drag. So let's turn it into a free body diagram. And again, hopefully you can see now how we can just combine all those together to get our free body diagram. Adding and subtracting of forces. Okay, when we subtract forces or add forces, we can make a resultant force. And it's the total force acting on systems. So if we look here, we've got 2 pulls, and we get 2 pulls like this, pulling in opposite directions, and they're the same size because the arrows are the same size. They've got 2 pull, but going to the right, okay? So if that's the case, remember the change of shape like that. We're pulling out with opposite, you're going to change that shape, Adding and subtracting forces. We can work out the total force, the resultant force of an object by adding and subtracting forces. And we'll go through examples of how to do that. Now, two identical forces acting in the same direction will have a different effect to ones acting in opposite directions. So let's have a look at examples of this. So we've got two acting in opposite directions, and we've got one where both of the forces are going in one direction. Well, this one's going to stretch, and this one's going to go off to the right, as you can see. So, adding and subtracting forces. Rules for adding forces. If the forces are in a line and acting in opposite directions, then you subtract them to get the resultant force. If they're in a line and acting in the same direction, you add them together. So one is subtract and one is add them. Okay? So let's have a look at this. So 40 and 40 acting in opposite directions. Okay? So we need to subtract the forces. So 40 minus 40 is 0. And that means that box shouldn't go anywhere. Now, if we look at the other one, 40 and 40, that means they're going in the same direction, which means you add the two together. Okay, so 40 plus 40 is 80. Let's have a look at this one. Got a rocket on top of a car. Okay, we've got some a force going forward here. Okay, your thrust essentially 500. You've got your air resistance, which is 150, and you've got the thrust going in the same direction here. So what do we need to do? Well, first of all, we need to add, and then we subtract. So if you look here, we add the 500 because it's going in the same direction as the 700. 500 plus 700 minus the 150, which is 1050 newtons. Okay, and that's your resultant force. Let's look at this bus. The bus has got an air resistance of 6,000 and it has got a thrust going forward of 6,000. So overall, it is 0 newtons. Now, looking at things like this can be one of two things, and we'll talk about this later in another video as well. But this could be that the bus is completely still, so not moving anywhere. Okay, essentially. Okay, because if something's pulling it back at essentially at 6,000 and then going forward at 6,000, it could not be moving anywhere. The other option for this is that it's going at a constant speed. Okay, so if it's got the same force going forward as it goes going backwards, if this object is already moving, it will be going at a constant speed. We'll talk about that in other videos. Now, adding and subtracting forces. If you look here, 50 is going down and 50 is going up. So 50 minus 50 is 0. Okay, and this cup's not going anywhere, not falling and not going up. Okay, so balanced and unbalanced forces are next. When the forces acting in the object are the same size, but in opposite directions, the resultant force is 0, and we therefore say it is balanced. Okay, and that means the forces are balanced, and it's known as being in equilibrium. So they're both pulling at 900, and so therefore this is in equilibrium, and the forces are balanced. Right, when they're not the same size, and they do not cancel, the resultant force is not 0, and we say the forces are unbalanced. Okay, and it's not in equilibrium. So there, for example, you can see that the team on the right has a higher force and therefore is going to pull it to the right. It's not balanced, it's not in equilibrium. What happens to an object at rest in equilibrium? Essentially, it stays at rest. Okay, in terms of this object. Now, how do you make an object at rest move? Well, you've got to apply a resultant force. So you've got to apply a force, and you can see it's 10 newtons here, so it's going to the right. Okay. Now, if we then remove that force, and we've removed that force, it will come to a stop. So it's just like you pushing it, okay, and then it moves, and then when you stop pushing it, it comes to a rest. Right. Does that mean we need a force to keep an object moving? Okay, well, that's a very, really good question. Remember I said in the last one that if the object is moving and it's got the same force going backward as it has going forward, it can move at a constant speed. If it's not moving at all in the first place, then it will stay at rest. Okay? So let's have a look at it here. If we look more carefully, and let's look at this in a bit more detail, you can see that there is friction between the cup and the desk. That means in this case, because there's friction, okay, because there's friction, we need to overcome that friction, which means to move this mug, we'd need to keep applying that force, okay? But now, that would also mean that if we are applying 10 and the friction is 10, you can see overall the resultant force would be 0 and this cup would not move. Okay? But if it was already moving and I was doing this, the mug would be going at a constant speed. Okay? So for example, it's already moving and you've got this. This is going to go at that constant speed if it's already moving. If it's not moving and the forces are balanced, okay, the mug will stay still. If it's already moving and the forces are balanced, okay, then it's moving at a constant speed. Okay? You don't require a resultant force to move at constant speed if the object is moving already. So a summary of that is going to be this. Resultant force will cause an object to speed up. A resultant force is not required to make the object move at a constant speed. You don't need a resultant force for it to move at constant speed. The object just has to be moving first. A resultant force will cause an object to slow down. Okay, so if that resultant force, the friction for example, is higher than the force you're using to push the mug, then it will start to slow down. Now, effect of balanced and unbalanced forces. Let's have a look, shall we? So we already know we've done this calculation here. Let's have a look and see what will happen with this. Okay, so what will happen with this is we've got a massive force going in this direction. So that means this will go in that direction. It will accelerate. It will go in that direction. If we look at this one, what's going to happen here? It's 0. So what's going to happen here? If this bus is already moving, it's going to move at a constant speed. Let's look at the mug. Okay, again, resultant of 0 newtons. The object will remain at rest. And this is a summary of resultant forces, and I hope this helps.